Now I'm going to start this one off here with a mathematical example, but it has some interesting, very interesting implications if you start taking this line of thought a bit further. Now, the example I'm going to give is very simple, but I want you to think about this for a moment. Now, we've got a magical bouncing ball, and the word magical is very important here, because even though the example I'm going to give will sound very familiar to somebody who is familiar with Newtonian physics, it is in reality just a mathematical abstraction in the mind. It has absolutely nothing to do whatsoever with physical reality. And this is not only because physical reality has been shown to be much more complicated than Newton ever imagined, but also because that's not what I intended for. It is just a visualization aid, so to speak, to the actual argument that I'm leaning up to. So if somebody starts coming back to this and going on about quantum mechanics, for example, I'm going to just slap your head. It has nothing to do with that. Okay, so this is a magical bouncing ball in a imaginary Newtonian universe, and it's magic because when you drop the ball and it bounces, it always bounces up exactly half as high as the height that it dropped from. So this ball is dropped from a height of 10 meters. So it hits the ground, bounces back up to 5 meters. It falls down, bounces back up to 2.5 meters, and so on and so forth ad infinitum. Then you ask two questions. The first question is, what is the total distance traveled by that ball during its bounces? And the second question is, how long will the ball bounce for? Now, let's first look at this intuitively. Now, every time the ball bounces, it is going to bounce again. Fair enough, only half the height, but there's never going to be a point where there's a bounce not followed by another bounce. So your intuitive response would be that the ball is going to travel an infinite distance and it's going to bounce forever. And you'd be wrong. Okay, the easier of the two is the distance traveled. It's fairly easy to calculate that, because you start with a distance of 10, but after that you basically get the same distance twice. So twice you add 5 meters, twice you add 2.5 meters. You can see how this works, because you bounce back up to 5 and then drop down 5 again. Then you bounce back up to 2.5 and drop down 2.5. So you get 2 times that distance every time. So what you're adding is an initial 10, and then add to that 10, then 5, then 2.5, then 1. And you can write this down as a sum, and it looks like this. And then you can say, like, well, imagine that that's called P, that whole sum added all together. Let's say that value equals a number P that we want to calculate, and then just say, like, well, double that number, which then has an impact on the sum on the other side. You work that out a little bit, and you realize that after a while you end up finding that 2 times P equals 20 plus P, and therefore P equals 20. If you then go back to your original sum, where you started with 10 plus this value P, and if we find P equals 20, which means then that the total distance travels must be 30 meters. So even though the ball bounces an infinite number of times, it only travels a total of 30 meters. But it's even weirder because it's going to travel. It's going to bounce for an amount of time. You can calculate this amount of time. You start off with the original distances taken, and using the formula 1/2 times a times t squared to find how far an accelerating object will travel within a certain time t, you can then turn that around and find how long it will travel how long it will take for an accelerating object to travel a distance. And having that done, we can plug that formula into the actual distances traveled, and we find that it will take the square root of 2 to travel 10 meters, and then it will take twice the square root of 1 plus twice the square root of 1/2 plus and so on and so forth to travel the remainder. Again, you can work that out. It's a little bit more complicated, but you need to double it again. You'll end up extracting 2 terms out of the actual formula. The 2 terms add up to 4 plus twice the square root of 2. You add that to the square root of 2, and you find that the total time spent bouncing is somewhere in the region of 8.24 seconds.